Okay, let's turn next about the standard errors of the regression and the coefficients. So why do we need standard errors of the regression and coefficients, and what does that actually mean? So any econometric analysis is based on a sample from which we need to infer about what the population parameters might be. So in the context of regression analysis, we want to test the hypothesis whether the regression parameters are statistically significantly different from zero. So we therefore need to have an idea about the sampling distributions of each parameter. And we have already seen that the regression coefficients are unbiased estimators. So what that means is if we were able to take an infinite number of samples from the population, and each unit of observation has, let's say, two characteristics, and we run a regression of one characteristic against the other, well, we will always get a slightly different intercept and a slightly different slope coefficient, even though we know if we were able to take a million gazillion samples, then the average of all possible intercepts and slope coefficients, that will be equal to the true population parameter, because we have already seen that the intercept and the slope coefficient, they are unbiased estimators. But what we ultimately get is we have a sampling distribution that we need to assume, and a sampling distribution we know by the central limit theorem is normally distributed, so something like this. And then we get a certain coefficient, like for example an intercept of 3 in our sample, and then we hypothesize that the true population mean, which is beta 0, for the true population parameter is 0. And then what we do in a hypothesis test, we essentially ask the question, how many standard errors is an intercept of 3 in a sample of a certain number of n away if the true population parameter is 0. And if this is very unlikely, then we reject. And for this purpose, we typically have an alpha, like an alpha 5%, and then we say, okay, if the probability of getting our sample statistic has less than a 5% probability of coming from a population with a hypothetical true parameter of 0, then I don't think that the true population parameter is 0, but you could have made a mistake. And that is what basically the alpha tells you, the risk that you reject the null hypothesis even though it is true. But anyhow, so in a hypothesis test, what I need to know is, if I get a sample intercept, for example, of 3 or a slope coefficient of 1, I need to know how far away is that in terms of standard errors from hypothetical population mean of 0. And for that purpose, as you know, we have to calculate typically a t-statistic, and then we subtract from the 3, in this case our sample average, the hypothetical mean, which is now 0, and then we have to divide by the standard error. So that's the purpose of the standard error. So it gives us the variation of the true sample intercepts if you were able to take a million samples from the population. Okay, so that's the purpose why we need that. And so let's actually start with the standard error of the regression, or the variance of the regression. So the variance of the regression is actually very similar to the variance of a variable x to its mean. So So for example, you remember that the variance of x can be written as the average squared deviations of all the observations from the mean divided by n minus 1. Okay, so that is the variance, but nobody wants to know what is the average squared deviation from something. People want to know what is the average deviation. So that's why we take the square root of the variance, and that is then the standard deviation. So the standard deviation is typically the square root of a variable. So that would be the standard deviation of x. So now when it comes to the variance of the regression, we assume we have a certain regression result. So maybe we have, so here we would have y, and here we have x, and then we have our observations. Maybe we have an observation here and there. And so we assume that there is an equal spread around the trend line. That's another assumption that we do. And there are like certain ways once we get into the how to run a regression and what are the steps. You know, there are like certain things we can do in order to make sure we get more likely an equal spread around the data, but that's for later. So now how do we calculate the average spread? Well, it's very similar. So the average variance, what we do is the formula for the variance of the regression. Let's call that variance x/y. Well, that is the squared deviations of all yi's, the red dots, away from the trend line, which is y hat. So it's not the mean of y, it is the estimated value. And now we have to divide by n minus 2. So those are the degrees of freedom. So the degrees of freedom are typically the sample size, n, minus the number of estimated parameters. So in this case, we have a regression. And what that means is why we have, in this case, if you have 6 observations, why do we have 4 degrees of freedom? What that means is, if I know, for example, let's say you know that the estimated trend line y hat is, for example, 3 plus 1x. Let's just assume. Then if we know that, we have 4 degrees of freedom, and what that means is, if, for example, we only know 4 observations, but we also know that the trend line for 6 observations is 3 plus 1x, I can actually fit those numbers in order to make sure that this regression line holds. And those could be any numbers. So it could be, you know, let's say these 4. And then I would know what the y is if with the estimated trend line is 3 plus 1x. Okay, so maybe it's a little bit complicated to explain degrees of freedom in the context right away, in the context of a regression. But it's very easy to understand if we examine it in the context of a mean. So assume we have, you know, a sample of, let's say, 3 kids, A, B, and C. And what I do know is that their average age is, for example, 8. So now if I note that the 3 kids average out to an average of 8, well, if for example the first kid has an age of 4 and the second has an age of 6, well, then I know that for the average to be 8, kid C must be 14. So when it comes to the mean, I have 3 minus 1 degrees of freedom. Or alternatively, if for example, I know the first kid is 10 and the second kid is 12, well, I know that the third kid C must have an age of 2. Otherwise the average won't be 8. So that's basically the logic of the degrees of freedom. So again, when it comes to calculating the degrees of freedom for the regression, we write it the variance of yi is equal to the sum of all the squared deviations away from the trend line squared, and then we average it out over n minus 2. And then if we take the square root of that, we get basically the standard deviation or the estimated standard error. And that is with respect to the sampling distribution. So, okay, so now we already know the standard error of the regression, which is here, and it's just the square root of the variance of the regression. And that will become part of the standard error of the slope coefficient and the standard error of the the standard error of the intercept. So let's just stop here and then continue in the next video with actually calculating the variance of the intercept coefficient. And for that we will need also the standard error of the regression. And the standard error of the regression and the standard error of the intercept and the standard error of the slope coefficient, those are important output details whenever you run a regression, and that is what any statistical software program will present to you. Okay, so but let's just stop here and then let's dive into the nuts and bolts of calculating the actual standard error for either the mean or for both the mean, the standard error for the intercept and the slope coefficient, beginning with the next video.